Okay. I'm Kevin Apreed, and this is lab number 5 in Physics 2211 attack. And surprise, I chose the Slinky, the falling Slinky model. For the details behind this experiment, the Slinky is held in air in like a stress position, and it's let go from the top simultaneously. The motion of both ends of the Slinky and the system as a whole is tracked and modeled. We model this motion using the tracker app from the given video, and we focus on the bottom part of the Slinky mostly, and it's like motion throughout the falling. And we perform calculations via Colosseum to create another model to compare to this video data from the tracker app. We compare and contrast these two models, and we offer reasons and explanations for possible discrepancies and where they could come from. The introduction, the purpose behind the lab as a whole is to analyze a system of our choosing and to put into practice the physics equations and the concepts we learned in lectures in group problem solving, and to have a chance to visualize it. The purpose of my specific choice, the falling Slinky lab, is to analyze the predictive motion of a falling Slinky and the influence of its surroundings on. For a preview of the result, the bottom of the Slinky is stationary in the air until the top, like we just did, snaps down, and they fall together until they reach the ground simultaneously. There's some physics concepts and formulas throughout this lab. Newton's second law of motion is at play, which states an object motion remains in motion unless acted on by another outside force, and an object at rest remain at rest unless acted on by another outside force. And an equation we used was velocity final equals F net divided by mass times time. And then another concept at play was fixed spring law, and these are the equations for it here. And for the position update, another equation we used was position update, and you can see that here. The initial conditions for the system, the system is a spring with a given mass and Earth acted on the spring. In surroundings, there was none. The initial velocity is 0, because 0 in all directions because it was dropped from a resting position. And the initial position from tracker are these values here. And the mass of the spring as a whole is 0.218 kilograms. For the tracker in the graphs for it, this first image right here, as you can see, is right before the Slinky was dropped. You can see like its initial position where the bottom is here and the top is here. And the second image is like halfway through the drop. You can see that the bottom is still stationary right here. It hasn't moved, but the top has came down as it's getting acted by the gravity and the spring force from the Slinky. And you can see this. This third image is at the end when they both hit the ground together simultaneously. And the bottom has moved, obviously. The flow script code, here's the initial conditions right here. Here's the calculation of the net forces right here and here. And this is just the visualization part of the code that would make a model. For comparing the similarities and differences of the two models, the orange line here is the observed and the blue is predicted. They follow the same trend on this line, except like the predicted model from the close script is more consistent along its path. As you can see that like the more discrepancies along this trend, you can see the light it is, which is to be expected from a computer model, to be honest. For some possible sources of air, human air interacting the center of the top of the Slinky using the tracker app to gather data, and outside factors not accounted for, such as like wind, affecting the motion of the Slinky being observed and tracked. What does it mean and what if? What does it mean? The bottom of the Slinky remained mostly stationary due to the force of gravity pulling downwards and the force of the top of the Slinky acting as like a spring pulling the bottom. These two forces canceled out. And so this caused the net force in the bottom of the Slinky to be 0, meaning it remained still due to Newton's second law until the top met it. What if we gave the top of the Slinky a spring and initial velocity downwards? This would cause the top of the spring to reach the bottom earlier than before, but it would not affect the results of the experiment. The bottom of the spring would remain stationary until the top reached it. In conclusion, the Slinky as a whole has a peculiar motion when compared to other objects, as the bottom of the Slinky remains motionless in the air from where it was dropped due to the effects of the spring force of the top section acting against the force of gravity at the bottom. In contrast, the top is propelled downwards by the gravity on the object as a whole and the spring force from the bottom section. Both the tracker and computer models support this conclusion despite the minor discrepancies.